Hey, thank you very much, Dr. Meekins, and thanks everybody for listening. Yeah, I hope you all appreciate my pretty absurd title. There's an undergrad at my university, Vanderbilt University, who's in the senior inorganic class, and one of their assignments was to make like a popular science article and make art for it. And so I got interviewed, and just today I got the article back, and it was really cool, and it had this title, which makes what I do sound pretty cool, and it had this pretty cool art. So thanks, Lauren, if you're listening, and thank you if you're not listening also. So yeah, smashing molecules together, mechanochemistry to make traditionally impossible compounds. I apologize for the mechanochemistry takeover of the open science presentations. We're just really opportunistic, and you got to kick us out if you don't want us around. So I wanted to talk a little bit about me and my background. So I'm from Bethesda, Maryland. This photo here is the National Institute of Health, and I kind of grew up. I don't think my parents' house is actually in this photo, but I think from another angle I could actually point at it. It's up on a hill, so that makes it a little easier. Um, but yeah, so I kind of grew up, some of my neighbors were scientists, and they would walk to work at the NIH. And when I volunteered there, I didn't walk, I was lazy, and it was, 100 degrees in the Maryland summer. So I took the metro, but I've always been kind of surrounded by and intrigued by science. And I did some research at the NIH and realized biology was not for me and decided to continue on with chemistry. And that led to me to McGill, where I did a bachelor's in chemistry and did a lot of research with Tomislav. And here you have a nice photo of the quad pre-COVID. And if you've seen the movie Get Smart, you may be familiar. This is the Red Path Museum, which they drove a car out of somehow in the new Get Smart, which is pretty wild. And here is our lovely chemistry building, Auto Mass. So I did a bunch of mechanochemistry with Tomislav, and that changed my life, of course. And I also had a bit of a taste of organometallics, and I thought it was the coolest thing, and I needed to find whoever did both mechanochemistry and organometallic chemistry. And that led me to Vanderbilt University, where I am doing my PhD with Dr. Timothy Hanusa, and I'm a fifth-year student. And right here is the chemistry building I work in. You can tell because it's got the stacks. This building also has some chemistry. It's got some stacks. And this building also has some chemistry. It's got some stacks. That's how you can tell. So in the Hanusa group, we're primarily focused on the structural, inorganic, and organometallic chemistry of basically the whole periodic table. But I'm more focused on the S&P block, what we call the main group elements. We like to use bulky allyl ligands. They're pretty interesting. This is the parent allyl. It is the smallest delocalized anion, so it's got some interesting properties and behavior. Right here is a figure that shows, as of 2013, all the crystallographically characterized bonding motifs that have been found with just the parent allyl and just main group elements. So just S&P block. And you can see there's a large variety that involve multiple allyls or multiple metals, and it gets pretty complicated and pretty interesting pretty fast right off the bat. But we like to use a bulkier allyl. Like I said, we use a bis-trimethylsilyl allyl, which has these two trimethylsilyl groups. And what this basically means is we've bolted 2 chunks of grease onto our allyl, which makes it about 2.5 times bulkier and provides both stability due to steric encumbrance and also solubility in solvents because it's basically grease, which for me is awesome because I'm working with things like potassium and magnesium. So the less salty we can have things and the more hydrocarbon soluble they are, the easier it is to work with. And some of the compounds we make are good initiators for polymerization, and we have a really great collaboration with Brian Long at UT Knoxville. He's been helping us do some really great work, and I've been lucky enough to have my boss help me learn a lot of computational chemistry, doing density functional theory, which is good because a lot of the compounds I make, they are pretty sensitive, and you make one thing and it might not survive long enough for you to do anything with. So we have to kind of do a lot of virtual chemistry. This is how I think about it. And so what I'm going to be talking about is some of the work I've been doing to explore the structure and bonding of main group elements and see if these have unique reactivity and unique properties that we can maybe potentially in the future leverage to solve some pretty big issues. So I'm doing a PhD in chemistry, so obviously I think chemistry is one of the coolest things in the world, and I can tell you a million ways that it affects your daily life and why it's really important and why you should care. But what I'm going to talk a little bit about now is why we should care about catalysts and catalysis and why it's important that we have more of them and more options. So one thing people may not realize is that most of the fertilizer we use is made of ammonia that is catalytically produced from nitrogen. And that lets us be basically 4 times more efficient land-wise with agriculture than we were in 1900. So that's one of the ways we're able to support our current population. And if we didn't have good catalysts and talented catalysis scientists, that wouldn't be possible. Another thing for people who like technical clothing or basically want to wear anything that's not cotton or wool, there's a lot of really fancy catalysis and chemistry that's involved in that to have the necessary level of control to have clothing with really, really fantastic properties. If you ever take a bus or drive a car or anything with an internal combustion engine, you're interfacing with one of these doohickeys, which is a catalytic converter, which basically puts all the exhaust through a bunch of rare, usually platinum group metals, and that does a bunch of things. Here I've got some of the chemical equations for that. Basically, it takes bad stuff and turns it into less bad stuff, and that's important because there's a ton of cars driving around, and they drive around a lot, and they drive around where people and plants and animals are. And you don't want some of these bad things, all this carbon soot, harmful carbon monoxide, NO species, and unburnt fuel. You don't want all of that going into your body or into the environment. And one thing that I didn't realize is that these, after about 100,000 miles, they lose about half of their catalyst mass. And this YouTuber, Kody's Lab, made a video where he basically swept up a ton of roadside dust and filtered, basically sieved it down to the finest particles. And from 150 grams of this fine road dust, he was able to refine out, 10 milligrams of platinum or palladium. And for one thing, that's really interesting. Yep, you are definitely losing catalyst from your car. And for another thing, that's not good because this stuff can be pretty toxic and harmful. So catalysts are awesome, but we want to be using catalysts that maybe are less benign or more earth abundant, because at the end of the day, everything gets thrown out and it's going to find its way somewhere we don't want it to be no matter what. And a really great way that catalysts are being used these days is in the production and development of pharmaceuticals. There's a big movement towards greener and more sustainable pharmaceutical synthesis. And one of the ways they're doing that is through using the use of catalysts, because a catalyst lets you use a substoichiometric amount of something. So instead of using one reagent per molecule, we're only using 20% here, or only 5% here. And this is cool, but if you know a little bit more about this, you know that these are homogeneous catalysts. These are catalysts that are dissolved in solution, and it can be really hard to remove these from the pharmaceuticals or the precursors. And what that means is that you have to work really hard to get this 5% of palladium out, because like I said before, palladium can be really harmful to the body, and you can't have that in consumer products. So kind of what I've been focusing on is figuring out if and how we can use more sustainable, more safe elements. I talked a little bit about palladium. Here is a graph showing how much the cost of palladium has increased from 2018, or basically 2019 to now. It's almost tripling. I haven't looked at what it is now, but I'm sure it's pretty high. And like I showed before, people like to use palladium, and it's really good at what it does. But if there's geopolitical issues, or if there's just a supply shortage, we're going to have problems. So what I'm kind of focused on is using these really, really highly abundant elements and trying to figure out if we can do chemistry with them that is maybe more along the lines of what we traditionally expect from transition metals. And that's probably going to be a long ways off. If you follow Nobel Prizes, there's been a bunch of Nobel Prizes for organotransition metal catalysis, and there hasn't been one for main group catalysis yet. So fingers crossed, but it's probably going to be a long time there's just such a head start for transition metal chemistry. And as I'll show you later on, this main group, organometallic chemistry, can be really challenging, and it's really important we develop new tools to make that possible. So I talked about mechanochemistry. I've used the word, but I should probably explain what it is. It's basically a chemical reaction that is induced by the direct absorption of mechanical energy that comes from a very famous Nobel Prize winning chemist, Wilhelm Ostwald. Basically what we do is we put, what I do is I put reagents in these jars or milling vessels with ball bearings, and I have an instrument that spins it all around, and that gives my chemicals the energy to react. And it's pretty cool because you might be doing solution chemistry and your reactions will take 18 hours or a day, but a lot of my reactions only take 5, 10, 15 minutes, and I don't have to evaporate 2 liters of solvent off. So it's much more sustainable in that way, in addition to using less energy. And there's a bunch of different, there's lots of variables you can tweak. You can use different materials, different types of jars. You can use plastics. You can use hard ceramic materials. You can use a copper jar to do copper catalyzed reactions. There's really lots of interesting things people are doing. But I want to note that the way my group was initially doing this was by having a round bottom flask with ball bearings in it, and you put your reagents in that and you spin it on a rotovap. And that was before my time, thankfully. It was pretty exciting because you didn't know if your flask was going to break or not, and you have to, this is inside a glove box, and if you don't know, you really do not want to clean up glass inside of a glove box. It's the last thing you want to do. So I want to show some cool examples of mechanochemistry that I really like. Here's a mechanochemical book called Hartwig Emanation from the Brown Group in the UK. And this is really awesome. Normally, this is a relatively air-sensitive reaction, I believe, and they can do it just in air. They can do make lots of different types of compounds with it, and the catalyst loading is really, really low. So that's pretty awesome. Here's a pretty unique example of synthesizing some gold nanoparticles, where essentially, normally you would need an external reducing agent, but because you're using a stainless steel milling jar, that itself acts as a reducing agent and allows you to have really nice, small monodispersed gold nanoparticles that are really, really challenging to achieve normally. Here's kind of a cover image focused on mechanochemistry from the European Journal of Organic Chemistry. I guess being a mechanochemist, I would consider it kind of a niche field, but we've been really lucky that a lot of publishing companies have been really receptive to it and really helped us hype it up. In this example from the Garcia group in Singapore, we're attempting to cyclize this extremely bulky phosphazane. This has tert-butyl groups, so they're extremely bulky and it's very challenging. And even if you heat it at 150 degrees for 24 days, it does not go. But if you just mill it for 90 minutes with a small amount of a salt additive, it goes very nicely. Another reason I like this example is because they have this 3-ball symbol, which my group previously, I guess, came up with. And a lot of people have adopted it as kind of a universal symbol for mechanical milling. So we're really proud of that. And kind of a similar example in terms of result, you can try to make this cool platinum square compound hydrothermally. So in an autoclave, it takes 4 weeks at 100 degrees. But if you grind it manually with a mortar and pestle, you don't even need a fancy mill or anything like that. You can get it in a similar yield in just 10 minutes. So mechanochemistry lets you do some really cool stuff really quickly. And I figured there may be some people who are not chemists in the audience, and well, if you're not an organometallic chemist, you may not really have a great idea of what I do day to day. I can tell you I did not, even though I did research for 3 years in undergrad. So basically, pretty much everything I work with is air sensitive and moisture sensitive. I mean, probably both, but we don't spend a lot of time figuring out which one it is, because usually if there's oxygen, there's going to be moisture and vice versa. So basically, this is a glove box. Inside of it is a purified nitrogen atmosphere. This is hooked up to a nitrogen canister of some kind. And the nitrogen inside is circulated through a circulator that has a catalyst that removes all of the oxygen and moisture. So what's inside of here is actually even higher purity than what you get from the bottle or the tank. So it lets you do some chemistry that's really, really, really sensitive. And you can see it sometimes because I've made some compounds that are very sensitive. And when you're working with them, you can see in the flask, it's decomposing from the top down. Even in the glove box, sometimes it can be challenging. So basically, I set up my milling jar. You can actually see it there. I didn't even notice that. I put my chemicals and my ball bearings in my milling jar. I clamp it and I take it out. I put it in my mill. I bring it back into the antechamber and cycle it 3 times and bring it back in. And then I open it up and see if I have anything that looks good. This was some tin chemistry, so it looks kind of gross because you always end up making a little bit of tin zero, which is basically nanoparticulate tin metal, and it's black. And my compound itself was kind of brown, so it's kind of gross. The chemistry I do is not solvent free. So I still need to use solvent to extract my compound, and I filter that, and then I evaporate that filtrate, and hopefully I make something that's cool. Here is a compound that's like a brown goop. For us, that's normal because, like I said, I'm basically using, canned grease as my ligand. If I make something nice that I want to have my friend Alicia in the long group do polymerization with, I will seal it up in a glass ampule and send it off. And if I'm really lucky and I grow some crystals, I will, bother our local crystallographer at like 6 p.m. and we will try to mount and get the crystal running before he catches the bus home. And if I'm really lucky, I will get a nice diffraction pattern like this. And basically, from these X-ray diffraction spots, we can back calculate. Basically, it's X-rays bounce. Well, a way to think of it is X-rays bouncing off atoms in a molecule. And so from that, we can back calculate where the atoms are in the crystal, and that's what your compound looks like. And we have a really great crystallographer, and he has always been super helpful when I'm working with all these extremely weird and sensitive compounds. So I'm very, very lucky to have him help me. And because what I do is kind of weird, I end up doing a lot of calculations to kind of learn more about my compounds and maybe, understand why they're sensitive, or maybe figure out more cool stuff I can do with them. And I use Gaussian for that. So as I said before, we use allyls. We use a bulkier allyl. It's much more fun. There's lots of different ways allyls can interact with metals. What I'm mostly going to be talking about is if something is eta-3 coordinated, so interacting with all 3 carbons, or eta-1 coordinated, interacting with just 1 carbon. Something that's really nice about the allyl is it basically acts as a reporter ligand. Based on how your metal interacts with the allyl, it tells you a lot about the metal. Is it electron rich? Is it electron poor? Does it want to interact with more things? Just all kinds of different stuff. And we have a pretty solid synthesis for this bulky allyl. This is a commercially available trimethylsilyl-propene, and we lithiate it. Then we quench it with trimethylsilyl chloride to get our second TMS group on there. We lithiate that again, and then we transmetallate with potassium terbutoxide. And this is soluble in hexane, and this is not. So it's very nice. You just crash out a lot of this from solution and filter it. And if you were really careful and didn't let any air moisture get in, it should be pretty much white. And I have done this a lot of times in my PhD. And this is a really nice ligand. It has helped us make some compounds that honestly a lot of people have been interested in and attempted to synthesize for a long time. So one thing we were able to make a few years ago was this first example of an unsolvated aluminum allyl, which surprisingly had never been done before. And it turns out it's really challenging. And these types of compounds are absurdly sensitive to solvent. And the reason is because aluminum is a Lewis acidic metal. And normally you have to use Lewis basic or coordinating solvents, and it just messes everything up because aluminum trichloride is very polar, so you need polar solvents. And you can't do a reaction like this in hexane or toluene. It just doesn't go. So something that the group is really interested in is S-block chemistry, like I mentioned. my boss's goal when he started was basically to put S-block chemistry on the map. And yep, I think he did it. He published the first organobarium crystal structure. I mean, tons of organocalcium chemistry. I mean, you name it, the guy's done it. But something that's kind of interesting is that there was never a crystal structure of just plain old, magnesium allyl. And it turns out that when you try to make a magnesium allyl with the parent allyl, it makes a really huge, essentially an infinite coordination polymer, and it's completely insoluble. And it's interesting. If you look in the literature, there's a lot of systems like this that you think somebody would have done, and maybe somebody tried, but it turned out it's basically not something you can do. So we took our bulkier allyl, which we refer to as A prime, and again, it's basically canned grease. So we said, well, hey, it was insoluble with the parent allyl, but maybe with our bulky allyl, it'll be a little bit better. So we do a standard solution route synthesis in THF at negative 78 degrees overnight. And you work this reaction up and you get what we expect, bis allyl magnesium, bis THF adduct. So 2 allyls, 2 THFs. You get a crystal structure. It's great. It's reasonable yield. But you can't do anything with it. It's not good for anything. It's not capable of initiating the polymerization of methyl methacrylate, which is like one of the easiest things to polymerize. You take the inhibitor out of methyl methacrylate, and it polymerizes itself. I mean, this compound is totally dead. And THF is such a strongly coordinating solvent, you can't pull it off no matter what you do. So we decided to try to use a less strongly coordinating solvent, diethyl ether, and you get the analogous compound, bis allyl magnesium, bis diethyl ether adduct. And if you are dedicated or have some very nice high vacuum equipment, you can pull vacuum on it for a while. I had to do this in my glove box antechamber because we no longer had a diffusion pump, so I cannot actually do real high vacuum. And you pull the diethyl ether off and you get this weird dimerized bis allyl magnesium compound, and it's pretty cool. It's got, each magnesium has 2 allyls sigma bound, and one of the sigma bound allyls is participating in a cation pi interaction bridging with the other magnesium. So we would call this eta1 mu eta2 coordination. Eta1 because it's eta1 to 1 magnesium, mu because it's bridging another, eta2 because it's eta2 with this magnesium. So this is cool. Definitely not what we expected, and it's a nice yield, and it gave a really complex NMR spectrum because essentially this bridging cation pi interaction stops everything from flopping around in solution. These are crystal structures, so it's basically a snapshot, but in solution, and even when you're doing solution analysis, it's essentially averaging over multiple states over time, which makes things complicated because what you see in solution is not really indicative of a single snapshot. And this actually turned out to be I'm not going to say it's a good catalyst, but it had interesting polymerization initiator properties, which I'll talk about a little bit later. And I've done some literature searching, and I found another example where somebody tried to make a desolvated magnesium allyl, and guess what happened? It didn't dimerize, it hexamerized. So we're kind of figuring out that magnesium really loves its solvent, and when you try to take solvent out, it gets, dare I say, angry. So this was 2009, and well, what can you do? There was a paper published in 2008 that said, a noteworthy feature of magnesium allyls is the apparent preference for eta1 allyl coordination, suggesting that eta3 coordination of the allyl ligand to magnesium is intrinsically disfavored. Okay, 2020, I think that's a bit of a cop-out perhaps, but there was no previously reported eta3 coordinated allyl on magnesium, so okay. This was really interesting to our group because if you do DFT calculations and you put 2 allyls on magnesium, they're perfectly happy being eta3. If we try to mimic more real-world experimental conditions and you add 1 THF to the magnesium, 1 allyl slips. And if you add a second THF, another allyl slips. And wow, that looks pretty similar to the actual crystal structure. So that's good because sometimes you do calculations and they don't exactly match up to what happens in real life because calculations are gas phase, 0 Kelvin, et cetera, et cetera. But basically from this, we figured out, okay, solvent is really playing a huge effect, and you can't do a reaction with magnesium chloride in anything except diethyl ether or THF or things that coordinate at that level, because magnesium chloride is a salt. You can't do a reaction with salt and hexanes. But I already told you that modern day we have mechanochemistry. So of course, the previous student Nick Reitmeyer and I work on this project, and we attempt to mill 2 equivalents of the potassium allyl with magnesium bromide. And if you mill it for 15 minutes and extract it with hexanes, you can grow a crystal if you're really lucky. I was only ever able to do this once, and thank goodness I actually grew, I think, 2 crystals in an NMR tube, and one we later found out was just like a potassium allyl that had precipitated out. But we got really lucky and picked the right crystal, and it was this lovely sheet that was not bisallyl magnesium. It actually has a composition of 2 potassiums, 1 magnesium, and 4 allyls. And if you zoom in on part of the fragment, you can see that this is the first example of a delocalized eta-3 bound allyl on magnesium. And we were super excited. The bond lengths are really good for a compound of this type to be delocalized. I mean, just fantastic. We were, overjoyed, all I can say. And this compound, it's a metalate because it has normally magnesium has a 2+ charge, but you have 4 allyls on it. So it has an overall charge of 2-. So you have to have the 2 potassiums to balance it out. And that puts it in this class of bis trimethylsilyl metalates, which we have some experience with, especially with divalent metals that commonly exist in the +2 oxidation state. We've seen this kind of conserved templated tris allyl metalate structure with beryllium, zinc, tin, and we were surprised that we didn't see it with magnesium, but hey, I mean, we got an eta-3 allyl. I'm not going to complain. And one reason it's conserved quite often is because this threefold cation pi interaction between the allyl double bonds and potassium is energetically significant, about 24 kcal per mole. And it's pretty cool. And there are some other groups that have made some metalate. These kind of things are known, but one thing we were really excited by is there's a paper from 2013 where essentially an analogous compound to my magnesiate was made with the parent allyl, and it was an extremely potent initiator for the polymerization of butadiene, which is a really, really challenging monomer to polymerize, especially with main group metals. Most cannot even attempt to do this, and this did it at 0 degrees in 1 minute. And it had, I believe, pretty good control over the microstructure. So we were really excited. Hey, we got a really awesome structure, and hey, there's a really similar, this compound is as similar to my compound as you can be just by looking at the composition. And so cool, we have a similar compound that's an amazing polymerization initiator. So how does my compound do? Well, we seal it up and send it off to Alicia in the long group at UT Knoxville, and she's very patient and doesn't complain when my stuff takes longer to get there than I say it should. And sorry, this is a bit of a data dump, but it turned out that my magnesiate is basically about as good polymerization initiator as the starting material, the potassium allyl. And that's still pretty good because the potassium allyl itself is pyrophoric and it lights on fire spontaneously in air. So it's nice if you can do chemistry as good as that and not have something that lights on fire spontaneously. But yeah, no tacticity control and similar or worse yield and polydispersity and molecular weight. But that's okay. And here's what I was saying about the bis allyl magnesium dimer. It has a high isotacticity enrichment, which means that it's neat because even though this is an anionic polymerization mechanism, it shows that there is definitely some type of impact of the metal and the structure of the starting material that's used to initiate the polymerization with. So cool. I spent a lot of time trying to think. So yeah, basically I got the crystal structure of this magnesiate in February of 2017, and this paper was not published until 2020 because basically it took us 3 years of thinking about and trying to figure out what was going on. And we didn't understand why we couldn't get bis-allyl magnesium, and we didn't understand why we were the only people who could make an eta-3 allyl and nobody else could. It's hard to just publish a paper that says, hey, we did something. You really need to contribute and say, hey, we did something because, and we understand why or why not, et cetera, et cetera. So something we like to use to analyze a lot of our compounds is this program called Solid G, which essentially you take a crystal structure or a calculated structure, and you basically put it in this program, and it kind of shines a light on it and sees how much of your metal is not blocked by your ligand. Or I guess in this case, how much of your metal is blocked by your ligands. So here you can see just the plain old calculated bis-allyl magnesium with the bulky allyl has a G complex value of 73.1%. So its coordination sphere is 73.1% saturated. And all of the other species that we've been able to isolate, the magnesiate, the THF adduct, and the dimerized bis-allyl magnesium, have a G complex value much closer to 90. So that's telling us that things with a higher coordination sphere saturation, you have a chance of isolating, and something with a much lower coordination sphere saturation may be too reactive, is our hypothesis. It's possible we're making plain old bis-allyl magnesium in situ, and because in mechanochemistry, everything is always mixing together, it can just pick up two equivalents of the starting material, and then you have your magnesiate. It's possible we are making our kind of often conserved tris-allyl metalate structure, but again, there's still potassium allyl around because it's all milling together, and you get your magnesiate. I thought, hey, okay, is there a way I can totally avoid potassium incorporation? And I looked at some papers, and it's like, oh yeah, dibutyl magnesium is a reagent, and it's pretty good at deprotonating stuff. So maybe our TMS, our bis TMS propene is relatively easy to deprotonate. So maybe we can do that, but it doesn't work. You get a really weird pink goo that decomposes when you try to pull vacuum on it or heat it. So I couldn't even isolate anything because you can't remove the solvent on it, basically. And it was annoying because there's this example from 2008 where essentially somebody bolts THF onto this bis TMS propene, and you add dibutyl magnesium, and it works perfectly. And I guess that's basically because it's like pre-coordinated, and it's just in the right spot that it's already there. And it's like your solvent is bolted onto your allyl. It's going to hold it in place because we know it's got such a strong interaction. So the other question, like I said before, is why we got an eta-3 allyl and nobody else did. And this was really tough because there's really few magnesium allyl complexes that are known and crystallographically characterized. And basically everybody was doing this chemistry with coordinating solvents. So pretty much all of them have solvents coordinated. We had a lot of ideas. Me and my boss just were hanging out in his office, brainstorming all the time. Is it symmetry? Is there charge symmetry? Is there charge separation? Do the negative charges have to be, separated a certain amount or in certain positions? Is it electron density? Are some of these ligands too strong and it's pushing, is THF such a strong electron donor that it's pushing the allyl off from eta-3 to eta-1? Or, is it coordination sphere saturation and all the solid G stuff? And we basically, after 3 years, kind of settled that it's just coordination number, which is, pretty funny because we had all these pretty intense high-level ideas, and then it turns out, oh yeah, your coordination number has to be 4 at max because that's how it works. And yeah, what we found is that all crystal structures with eta-1 magnesium allyl bonds are at least 4 coordinate. So if you were to go eta-3, it would push your coordination number to at least 5, which is not what magnesium really wants. And you can see here that this eta-3 allyl really is a 2-coordinate ligand, because if you do atoms and molecules calculations, you can see these, it's got 2 bond critical paths, one from each terminal carbon, which represents a critical amount of electron density that could be indicative of bonding. And so we came up with this kind of formula for how to have an eta-3 allyl. And basically, you need your X, Y, and Z to match up to be equal to or less than 4, because if it's more than 4, this is essentially your coordination number. And if your coordination number goes over 4, your eta-3 allyl has to slip back to eta-1. And one of the ways we rationalize this is that magnesium, can only be 4-coordinate to have a more covalent interaction, the eta-3 interaction, because that it can only be sp3 hybridized if it's going to have that type of covalent interaction. And this just took us a long time, and it was really tough because there's only one example, so there's not really a whole lot we can compare it to. So I'm just out here doing hundreds of calculations. So one calculation that we did that we thought was really effective at showing this situation is, here you have a lithium PMDTA eta-3 allyl complex. So you have a coordination number of 1, 2, 3 from the PMDTA, 4, 5 from the allyl. And if you change this lithium to a magnesium and you do a geometry optimization, the allyl immediately slips, and yep, we have a coordination number of 4 here. So that kind of, again, fits in with our formula, and I've done lots of calculations and they all fit in with our formula, which made us happy. So I hope I've showed that metalates are often more active than their neutral species. In our case, unsolvated compounds are much more active, especially if they're main group species. Mechanochemistry gives products with unexpected stoichiometry, and that's really cool, even if it can be challenging. And if you're ever dealing with systems like this, solid G can be a really good way to rationalize stability, or maybe the feasibility of some types of compounds. And yeah, sometimes the simplest answer makes the most sense. So it's a good idea to start with that. So that was a big project for me. And after that, I got to try to work on some other stuff. So what's better than magnesium? Well, why not calcium? It's heavier. I saw a research group tweet about calcium hydride compounds, like music heavier is better. And I thought, wow, that's fantastic. So magnesium was great. Let's do some stuff with calcium. My group has done a lot of work with calcium. We've made some solvated allyl compounds. Here is the bis allyl bis THF calcium compound. And you can see here that even with 2 THFs, both allyls are still eta-3 coordinated, because calcium has a strong preference for eta-3 and it's just bigger, so it can support a higher coordination number. And this was cool, and it's still active for polymerization. So maybe if we make it unsolvated, it'll be a really great catalyst. However, organocalcium chemistry is really, really, really hard, and that's why you don't really see a whole lot of it. For instance, trying to do heavy Grignard chemistry, so calcium aryl halide, calcium organohalide stuff. You can't really start with calcium metal the way you do with magnesium metal. If you've done an undergrad degree in chemistry, you have probably done a Grignard. I mean, I activated a magnesium Grignard in my undergrad organic lab by hand. It's really not that hard. But if you're doing it with calcium, you basically need to start with nanocalcium, and that's often done by, condensing calcium vapor, which sounds like a nightmare. And if you are able to make an organocalcium compound, they're extremely reactive and will basically immediately cleave whatever solvent the chemistry is being done in. And if you're able to get past that, these compounds are extremely ionic and salt-like and are extremely insoluble. And if you're still even able to get past that, they're even more oxyphilic and interact even more strongly with ethereal solvents than magnesium. So it gets really bad really fast. And here's an example where, yes, you are a really talented chemist and you've condensed calcium vapor and you're doing this chemistry, And you have to keep this compound below negative 30 degrees Celsius, because if it goes above, it'll just basically eat calcium and the calcium will eat the THF and decompose. So yeah, this chemistry is really challenging. So of course, I thought, hey, I don't need solvent. I don't need THF. This should be easy. Let's go. So I took 2 equivalents of my potassium allyl and calcium iodide and did a planetary mill grind at 600 RPM for 15 minutes with a toluene extraction. And I got an orange oil, which, okay, pretty reasonable. These types of compounds often interact with arene solvents like toluene, and you get charge transfer, and it's got some color. It's not boring like some people may think. And I took an NMR, and basically what I'm looking for is a TMS signal, a doublet, and a triplet. And I have some experience with these types of systems, so I know that this is probably an unresolved doublet, and this is probably an unresolved triplet. And this is a neat spectrum because this is one of the furthest allyl triplet shifts I've ever seen. It's actually past the residual solvent signal, which is very, very uncommon and usually points to some unique structures and properties. And we got a crystal structure of it. This is the unsolvated crystal structure that the previous student, Nick Reitmeyer, got. I got 2 solvated forms also, the methylcyclopentane and the deuterobenzene solvate. And what you can see, or well, what I'm going to tell you is it's a polymeric, it's a coordination polymer, and it has a 3-to-1 allyl to calcium ratio. And so it's got it's a calciate, potassium, calcium, 3 allyls. And usually these types of compounds are fluxional. That means when in solution, everything is basically scrambling constantly. And you usually will only see one type of allyl, but for the magnesiate, for example, you do actually see 2 different allyl signals. So this is not the most unreasonable thing. And you could say, hey, it's unresolved because it's fluxional, and at lower or higher temperature, it'll resolve. Okay, cool. That makes sense. You can convince yourself of that, or I can convince myself of that. But like a good chemist, I do my due diligence and say, okay, 15 minutes is a start, but let's try some different grinding times. And if you grind for 5 minutes, you see that you get one of the triplets, one of the doublets, and a TMS singlet. So that's cool. And if you grind for 20 minutes, you again get that FAR triplet, a doublet, which is resolved this time, and a singlet. But wait a second. This doublet is actually really shifted from where it was before. This one before, this one before was like 2.4, and now it's past 3. So that's interesting. And yeah, basically what I figured out is that there's actually 2 compounds, and there's obviously some type of mutual interaction that causes there to be a shift in at least this doublet when they're together. So basically we can make, and I figured out that these compounds are indeed what you make, that I figured out that the 15-minute product is indeed, I figured out what's going on here. If you mill for 5 minutes, you get the initial product if you extract with toluene. If you re-extract this residue with hexanes or attempt to crystallize it, and you grow crystals and you take an NMR of it, you get product 2. So that means the crystal structure we got has to be product 2, because you cannot grow crystals of product 1, unfortunately. Product 1 is not stable in the absence of arenes. So basically any handling causes rearrangement, including letting it sit, including attempted crystallization. And I have done this reaction a million times and tried a million different crystallization conditions, and you get one big, nice crystal of product 2. I found out that measuring very unstable things is hard. We know that product 1 rearranges in the absence of arene solvent, but because we don't have a crystal structure of it, I was kind of thinking if there's any kind of neat experiments we can try to do that will give us some more information. Maybe if we can do some kinetic experiments and figure out, what order interaction does it have with arenes or with non-arenes, and, try to figure out some type of structure from it based on that. So I basically took a bunch of NMR tubes and made some deuterobenzene and hexanes mixtures of product one. And what I found out is that everything except 100% deuterobenzene solution rearranges before you can even get to the NMR room. But what I did find out is that you can basically monitor this over time and see that there's essentially no rearrangement from product one to product two until about 40 something hours. And then this is potentially an autocatalytic process, which is pretty common when you see something that has a very long induction period, and then it has this kind of potentially exponential curve. I would have to do this experiment multiple times, and unfortunately, these compounds are so air sensitive that towards the end of the run, there does start to be decomposition, and so it's really tough to actually get really good numbers. And so this is actually in the SI because of this paper, because it's just this is essentially qualitative data. So we know what 2 is, but we still kind of need to figure out what 1 is. Luckily, we do know a certain amount. It seems to have the same composition as product 2 because there's no precipitation or decomposition over the course of the rearrangement itself in the solid state, for example. We know it definitely interacts strongly with arenes because it's colored in arene solutions, and it decomposes without arenes. So it's basically holding it together. And again, it must have some type of structural rearrangement with the arene removed, and the proton NMR shift being past the residual solvent makes it likely that there's some amount of 801 allyl character. For instance, the sodium zincate has three 801 allyls and has a triplet shift at 7.59 ppm. So we had a lot of ideas and a lot of hypotheses, and what we kind of settled on was this calcium allyl with one eta 3 and two bridging eta 1 allyls where they have cation pi interaction with potassium, and the potassium also has a cation pi interaction with potassium. And that makes sense because normally you would have the 3 allyls interacting with the potassium, and maybe now it's essentially starved for electron density, and so it's really happy to hang on to this benzene. And it makes sense that this would be unstable because we know that calcium does not really favor eta 1 allyls. So basically, this potassium and this arene are kind of holding everything together. And yep, if you do a calculation on this structure and remove the benzene, it indeed does rearrange, and one of the allyls goes from eta 1 to eta 3. So this was about as good of a model as we could get, and we were pretty happy with that. So basically, you take 2 equivalents of potassium allyl, grind it with calcium iodide. If you do it for 20 minutes, you get product 2. If you do it for 5 minutes, you get product 1. This is what we think it's like. Like I said before, I did a ton of reactions to try to get crystals of this, and they're so small and so sensitive. And again, over time in arenes and even faster in hexanes or in the solid state, it will rearrange. Of course, we want to see if product 2 at least is a good polymerization initiator. It's an oil, but it solidifies and it's not terrible to handle. Again, what we found is that it is a really good methyl methacrylate polymerization initiator. We actually had to go to 1,000-to-1 monomer to catalyst loading because Alicia called me when I was visiting my great aunt, and she told me that when she added the catalyst and turned back around, the solution had totally solidified. So, whoa, this is some hot stuff. And that's really awesome. And just like the solvated calcium allyl, it does have it does give isotactically enriched polymer. So that's cool. And again, shows that perhaps the calcium does have some interaction, even though this is an anionic mechanism. And another thing that's pretty unique is that we essentially have the same activity at room temperature as at negative 78 degrees. And this is a type of phenomenon that people are interested in called temperature independent catalysis. It's kind of a buzzword apparently. So we were excited to see that. And it's such a good methyl methacrylate initiator. we thought, okay, what else is pretty tough to polymerize? And instead of doing butadiene, we used isoprene, which is basically butadiene with the methyl group. And it's nice because isoprene is a liquid at room temperature, unlike butadiene. Um, it sounds like doing butadiene chemistry is challenging, and it's probably not fun to do that in a glove box, which is where you would have to do this. But what we found is that this calciate that we made is, as far as we know, it's the best isoprene. It's the best calcium isoprene polymerization initiator. 100% yield at room temperature over 12 hours. It appears to give no 1,2 polymerization. It has a nice polydispersity, and it's kind of tough to say that much more because these other catalysts that have been used, they had to do it at higher temperature, and isoprene is a gas at those temperatures, so you can't even get a yield because you don't know how much isoprene is being polymerized and how much is just evaporating. So good for us. So I hope I showed that mechanochemistry opens up a new world of solvent-sensitive chemistry. This is a graphical abstract showing that mechanochemistry and ball milling allows us to make first contact with new types of species. Group 2 chemistry is unpredictable without solvent. It's kind of unpredictable even with solvent. Mechanochemistry favors higher coordination sphere saturation, like I showed with magnesium chemistry. And because everything is always mixing together, you can incorporate excess starting material or byproducts, which allows for interesting mechanisms or materials to come out of it. When you're not worrying about solvent, there's a lot of other smaller interactions or influences that you have to worrying about, which is, it can be challenging, but it can be really rewarding, and you can really learn a lot about your systems. All of the chemistry I've showed is basically done with the milling instrument at as high output as possible, 600 RPM. What this means is that often what I isolate from these really fast reactions are what we call pre-equilibrium products. These reactions haven't had time to go long enough to equilibrate, especially stoichiometrically. So it'd be really interesting to do all these studies, but with lower milling frequency and longer time, for example, and see if you're able to isolate other types of products. And it's hard to say how much of this is really applicable to other systems. All of the chemistry I've done has been really unique. Even the magnesium and calcium has been quite different. And I've done some other chemistry. Tin is a whole different story, and that's still main group. So hopefully there are a lot more people out there who want to do this kind of work, and we can learn a lot more and try to make some broad generalizations at that point. So I'd like to thank you all for listening, and all my group members and the people who've collaborated with me and helped me, especially my crystallographers, who all work really hard to work with the really weird and sensitive stuff I hand them, and our polymerization collaborators who have done a lot of really nice work, and of course funding, which has allowed me to do this chemistry and go present work and have fun at conferences. And it's been really great to work with all my coworkers, and I've learned a lot from them. And I've definitely, it's probably cliche, but I've definitely learned a lot working with some of my undergrads. I've been really lucky to have some talented undergrads here. Kev and Hogan and Grant were the ones I worked with directly, but Lanisa and Saki were really, really great to hang around with too. So I guess that's the end of my presentation.
Awesome. Well, thank you very much. That was super interesting. I figured it would be, but that was really cool. And so we have a ton of questions, so I'm just going to go ahead and jump straight into them. First, so when you when you started talking about the magnesium work, I think on the very first slide you immediately got some questions, and you actually had the same question asked by two different people at the same time,
Uh-oh.
which is pretty great. Uh, the first one to get it in was Carter Cole. He beat out chemist Craig, but they both wanted to know basically could you for the diethyl ether adduct, could you azeotrope it off, and that was the way Carter phrased it. And chemist Craig asked basically could you remove the THF or other or ether ligands by co-evaporation with something like toluene.
Oh my
Um,
gosh. I actually tried that and it's a really funny story. Well, it's kind of funny in hindsight, but it was tragic at the time. So we have these really weird azeotropic distillation setups, and I like dried one in the entire an entire one in the oven. And I told our crystallographer, who's my committee member, Dr. Schley, I was really excited, like, yeah, like I'm gonna set up this azeotropic, distillation and get rid of, desolvate this compound, and I don't need a high vac. And he looked at it and after 5 seconds said, "There's no way you're gonna get this thing in the glove box. You're gonna break it." Well, I was able to get it into the glove box. I was not able to get it out of the glove box.
oh
Um,
man.
I ended up trying it with my own, just kind of like, assembled out of glassware setup. And
Yeah.
it did not really work. And these compounds are so sensitive. Like, you really, like, if I like this synthesis here for the bis allyl magnesium,
Hmm.
bis THF adduct, like if you leave it on the Schlenkline for 2 days, it decomposes. These compounds are so sensitive. Like, you can't do like a 12-hour reflux on the Schlenkline with them. So
Hmm.
I did try that, and it basically just all decomposed.
Okay. Carter wants would like to talk offline. I believe he's joined the Discord. So that might be a good chance for you to chat with him. I think he has some ideas for how you might be able to do it. Um, hopefully maybe you guys can work something out there. Um, so this was a question that popped in my head, and I'm realizing now I was probably thinking of manganese. But I'll go ahead and ask it anyway.
Done that too. That's okay.
Yeah.
So yeah, our magnesiate is actually analogous to a manganese structure. Can you see my
Okay.
presentation still?
Yeah, sure can.
Oh yeah. So this is I took the reference out, but this is actually isomorphous to a manganate.
Oh,
But
okay.
I wasn't the first person to make it, but I did it in a rotation project, and yeah, I mean it's great. High spin manganese 2. You got 5 unpaired electrons.
Okay. So, all right. Well, then now my question feels less stupid. Maybe. All right. So, does the valence of the metal cation affect how it reacts with the alleles? So like let's say the magnesium is not really going to change from 2+, but let's say the manganese. If you could hold it in, say, instead of a 2+, like if you put it into a 3+ or a 4+ valence, would that affect how it coordinates? This is kind of I'm outside of my my knowledge base here, so that may be a very
That
simple question, but
No, that's a good question. It turns out that basically all transition metal allyls are eta 3
okay.
because of d orbitals. Magnesium doesn't have d orbitals. Tin doesn't
Hmm.
really have d orbitals that do anything. So with the
Okay.
main group elements, you don't really have directional orbitals that are influencing this bonding. That's why it acts much more as a reporter ligand, because it's going to do whatever it wants to do. There's no d orbitals, you know, doing all the MO diagram stuff that you
Okay.
see if you look up allyl chemistry in a like physical organic textbook, for example.
Hmm. Okay. So Chemist Craig wanted to know if you have tried exchanging the potassium cations with something more organic-y, like a tertiary ammonium. He's not sure what it would achieve, but I think he's just curious.
Um, the Okuda group has definitely used like ammonium salt starting materials, and it's cool because it lets you do some interesting chemistry. Um, we have only see the problem is we have to use this basically organopotassium salt.
Hmm.
You can use the lithium and the sodium, and for instance with zinc, we've got structures and NMRs of all potassium, sodium, lithium,
Hmm.
but it's just really hard to isolate. It's hard for me at least to isolate the allyl with other cations, and I've
Okay.
never. I mean, I don't know how I could. Maybe I could do some thinking and do some research, but I'm not exactly sure if I could make like ammonium allyl starting material, for example. I mean, you can do exchanges probably, but I would have to
Hmm.
think
Okay.
after the fact. And I had a whole project where I was trying to use like 18 crown 6 and stuff, and it turned out to be really weird and really messy, and I just made a lot of radicals, and it was not pleasant or easy to work with.
That's fair. Yeah. Yeah. Anytime you just got radicals floating around, that's not going to be good.
pretty, but
Yeah.
doesn't help you do stuff. It doesn't help you do stuff, at least.
Yeah. Oh, okay. So Carter wanted to know if, and again, my apologies, as a as a chemical engineer, I don't know some of these abbreviations. Can trimethyl silane be exchanged for CH bis trimethyl silane, and could to basically bulking it up further to try and help get that A to 3 coordination under a wider range of conditions?
So we have done a small amount of work with differently substituted allyls.
Mm-hmm.
I think we tried to basically put like bis-trimethylsilylamide on the allyl as a substituent. I have my coworker Isaiah. Some of you already saw talk. He's doing some other bulky allyl synthesis, and it looks like they're making some good progress.
Okay.
We've tried the tris-trimethylsilyl allyl, but what we found is that it essentially gives you compounds that have the same structure as bis-trimethylsilyl allyl, but then they're so sterically encumbered. Chemistry bulkier is better for sure.
Yeah. All right. Let's see. Carter had asked about giving a talk purely about mechanochemistry, and I pointed him to the two previous. All right. Let's see. Carter had asked about giving a talk purely about mechanochemistry, and I pointed him to the two previous talks, but yeah, I think I agree with Carter that the mechanochemical process is really cool. So he also suggested to prove autocatalysis that you were talking about, you could try doping in a little bit of the product at the start, but he wants to know if that's possible prior to the decomposition.
It is so, it's basically an oil. It's so hard to measure or weigh stuff out with any like real consistency, at least in our glove boxes.
Mm-hmm.
And yeah, like I said, I definitely am not saying this is autocatalysis, but it fulfills a small amount of criteria that point us towards that it may be a partially autocatalytic process. Wow, that's the most qualified statement of all time.
No, I mean it. I could see where that's a reasonable thought, just based on the fact that once it starts the decomposition, or not decomposition, but I guess the transition, it does seem to just carry on pretty
That's a
much
really
on
good
its own.
idea, actually, and especially because here you can see that it's not absurdly fast, right? It's not going to rearrange by the time I get to the NMR. So even if I have it a 50-50 mixture, then you still, you have hours and hours. So that's a really good idea, actually. I never thought about doing that. This was like literally the last thing I did before our lab closed down.
Okay, that'd be good. So maybe that'll help answer the question then.
Yeah, thanks, Cole. That's a really good suggestion.
Yeah. I'm sorry, and that was actually, to give proper credit, that was Chemist Craig. Sorry, not Cole.
That makes sense. Yeah. Autocatalysis is a huge systems chemistry thing.
Okay. And he said, he also noted in the chat that if you want to talk offline about it, and he is also in our Discord, I believe. So,
awesome.
Yeah. If he apparently he says that's what he does these days. So,
yeah,
sounds like you guys might
Dr.
be able to
Craig.
chat some more. Okay. Carter would like to know if there's any evidence of paramagnetic character in any of your compounds.
Not these ones. I've definitely made some things. Yeah, I mean, I wish I was making magnesium 1 or calcium 1. That would be so awesome. I've made, like I said, when I was working with trying to do 18 crown 6 and some other kind of crown ether cation encapsulation stuff, I got stuff that was pretty funky, and I don't know for sure if it's paramagnetic, but it's possible that I've made some weird stuff that hopefully somebody, a future student, will have some time to revisit, and the desire.
That'd be great. See, Carter also wanted to ask about. Oh, actually had a suggestion here. Said it's not a question, but if you have very small crystals, apparently Stanford Synchrotron Radiation Laboratory is trying to expand as a user facility, Apparently, they can do ultra fast XRD, which may allow you to get the diffraction on the small crystals there.
Yeah, I signed up actually for like the what's the X-ray source at Berkeley? The synchrotron X-ray source at Berkeley.
Okay.
Whatever that's, I don't remember, but I signed up for that because I was hoping that maybe, yeah, I actually would be able to. I have a friend who worked in the long group at Berkeley, and she does all their synchrotron experiments, and I was thinking, oh, maybe she could maybe squeeze one of my
Yeah.
experiments in. But yeah, the crystals are so small and they desolvate so fast. I mean, I was doing everything. I was trying to mount stuff with I was using silicon grease dipped in toluene. I was
Mm-hmm.
using capped on X-ray tape. I mean, literally everything that me or the X-ray crystallographer could think of. We were trying it, and this stuff is just so sensitive. I mean, if you've ever
Mm-hmm.
done this type of crystallography, you have stuff in oil and you pull it out and it basically like fizzles away as you pull it out of the oil. You can see it. It's just the worst.
That's crazy. I have not personally ever worked with anything that sensitive. I've worked with some things that were, you know, unstable, I guess, but certainly not to that extent. So I can only imagine trying to not only take the measurement, but have enough of the product to actually do that. That's not an easy
Oh
thing to
yeah.
do.
I mean, it was ridiculous. There was like probably a 3 week period or a 4 week period where at the beginning of my time at Vanderbilt. I'm
Hmm.
at Vanderbilt, by the way. I didn't mention that enough. So sorry to all the Vanderbilt people. Um, uh, yeah, there was a period for probably about a month where every time I brought my crystallographer a sample, he would say, "Wow, this is the most air sensitive thing I've ever handled." 4 days later, wow, no, this is the most air sensitive thing I've ever handled. And he's really skilled. He has done a lot of stuff for a lot of groups,
Hmm.
and yeah, I really appreciate him being so patient with me.
That's awesome. That speaks very highly of him. Let's see. So, Chemist Craig also has suggested for the for the reaction you showed near the end with the isoprene, I think it was. He suggests that you could also try dimethylbutadiene, which has a higher boiling point than isoprene.
Hmm.
So that might be
Yeah, that's a
another.
that's a good suggestion. Yeah, I guess I should have clarified that this other stuff,
Mhm.
the sec-bule and the DMAT and the fluorinol compounds was done by a different group. So,
Yeah. Okay. Yeah, that might just be maybe a good option as well.
mhm. Yeah, that's
Uh,
that's a good idea.
yeah. Let's see. Okay, and then the last one we have here, Craig wanted to know if you are familiar with the work of Robert Mulvey and Ava Hevia. It says their S block synergistic bond activation stuff is really cool, and he thinks that maybe your bimetallic system could do something similarly cool.
Oh yes, those are definitely two of my favorite chemists out there, and
Okay.
I followed Dr. Hevia's work. I know she moved out to Switzerland like last year, this year. Like, oh
Mm-hmm.
yeah, I keep tabs on them, and they do. Yeah, her work is so inspirational. Like I talk about doing, catalysis and doing cool reactions, and
Mm-hmm.
she's out here doing like, oh yeah, like that stuff. Just add sodium and iron together. I mean, their work is so ridiculous. Like they're doing all this like basically like sodium doped lithium and all
That's
these
awesome.
kinds of really unique chemistry that you wouldn't think these things you wouldn't think make a big difference, but having 2% sodium in your lithium makes
Mm-hmm.
the chemistry go like a million times faster. It's really fascinating, and they must be the most fastidious chemists of all time. It blows my mind.
That's really cool. I'll have to look into that. I mean, again, probably way above my head in terms of what I fully understand, but that sounds really interesting. I appreciate when people do that really fine tuned work where they're kind of saying, all right, look, we know this works, we know this works. What happens if we start tweaking it a little bit? And, can we make it better? And that's really cool. So I think I guess I'll give everybody a chance to ask any more questions they might have. This was a fantastic talk. This is really cool. It's another really interesting angle on it too, because we had Tomislav kind of explaining very broadly what mechanochemistry can do and some of the work he's doing. We had Isaiah talking about his work, and now we've got yours as well. And this just really, it's really interesting to see the breadth with which you can explore the chemical realm, the realm of synthesis with this technique. Because, like I said, until Isaiah gave his talk, I honestly wasn't aware of it as a field. So this is really fascinating. Another
Yeah,
fantastic talk.
thank you so much.
All right,
I'm
so
glad you enjoyed it.
oh, absolutely. I think, like I said, you saw the number of questions you had, so you obviously inspired a lot of interest with that. Oh, Chemist Greg says he's got an iron lithium paper out for review right now, and it was actually inspired by the likes of Mulvey and Heaviest, so keep your eyes peeled for that.
Yeah, I actually almost did. So in my program, we have to do a fake grant proposal, and I actually almost did one. I ended up choosing something else, but I almost did my fake grant proposal on a molecule that you can only make with Dr. Hevia's methodology, which is great because this is really awesome work, and there's this one compound I really want to make, and this is
Yeah.
the only way you can make it. Whoa.
Hey, all right, that's cool. Oh, you never know. Maybe you'll get a chance to put that out for an actual grant at some point. That'd be pretty cool.
Yeah, that ferrate chemistry is so cool.
Yeah. Hey, you know what? Don't knock it. You never know. Well, I think that's all the questions we've got. And so, if I could get you to hang around for just 1 second, we'll talk just a little bit more. But I do want to thank you again. Like I said, it was a super interesting talk. It covered a lot of really cool stuff. I'm excited to see what else you end up doing. And I'd like to thank everybody that came out tonight. And especially for the great questions. We had a fair number of people out here, so I think you had said maybe your family would be watching. I think they were.
Hey, awesome.
We had a lot of viewers, so that's very cool. But I do want to thank everybody for coming out. I say again, I'll throw the link for the Discord into chat one more time. Like I said, if you're in any kind of science, it doesn't have to be like a hard science. You are welcome to join up with that, and we'll be happy to have you. And there will not be a stream next week because it will be Christmas, and I hope you all have a great holiday break. Yes, Merry Christmas to everyone. So, like I said, won't be a talk then. We are still looking for somebody for January 1st. So if you are new here and would like to present, or if you know somebody that might, feel free to send them my way. They can find me on Twitter at Meekins Lab. Shoot me an email, meekins@sc.edu. Any of those is fine. And so I think that's everything I've got for now. So I will say, have a great weekend. Please wear a mask, and we'll see you, I guess, in 2 weeks. So have a great weekend, everybody.